Goed. Okay, it's 1:45 on a Tuesday afternoon. Welcome students to the 11th lecture on Multibody Dynamics B. If you look at the schedule, let me check the schedule, the lecture schedule, then this should be like the last lecture, right? Let me see, the four last. So today is May 27, then next week I have June 2, and then the final one is June 9. So still 3 lectures to go. Okay, today's topic. Today's topic is rotation matrices, angular velocities and Euler angles. And if time permits, I will also start with Euler parameters. It's chapter 19 in the book. But of course, before we begin with the contents, first we're gonna do a short Kahoot quiz. Okay, so everything is running. Let me get back to this guy. Yeah, okay. Kahoot, where art thou? Should be here. Number 11. It's classic. No sound, a little bit sound. Yeah, there's the pin. And I really encourage you to discuss. It's a bit difficult, of course, in online. However, students can be very creative, also with the homework and the WhatsApp groups and all kind of social media. So it is possible, even when you're sitting remote, to discuss your answers. Now, if somebody says in the WhatsApp group, this is the right answer, you should be in doubt. I mean, usually you're more right than the other one is right, right? And in the end, it's not about getting the right answer, but it's getting about the answer right. I have 85 watching in the live stream, or 84, and 94, 95 players, so that should be the max, I guess. Some late coming in. Yeah, that's how life is, right? Sometimes you're a bit late. Okay, let's start the quiz. 5 questions again. 1 single answer. It's about how many unique constraints there are on a rotation matrix. Shouldn't be too hard. We call it in Dutch inkoppertje. And because of the live stream, I also gave all the questions a little bit more time, I think 90 seconds. So you have just enough time to answer. Even the easy ones. Indeed, most of you are correct. Although you think you have 9 constraints, the thing is symmetric, so you end up only with 6 unique constraints. Those who say 3, please read the book. Okay, next question. The angular accelerations are, for this you will need the order equation of motion for a rigid body. It's given that there's angular velocity, mass moment of inertia by means of principal axes, and there's no torque, and then you can determine what are the angular accelerations about those axes. You have enough time, you have 120, I gave 120 seconds, so just take pencil and paper, scribble, calculate, or use MATLAB or any other thing. You can do it on pencil and paper, I guess. Okay, very good. The majority has the correct answer. Wasn't that hard. For those who have the wrong answer, just look at the problem again and redo the calculation. The order of rotation was, so you see here a rotation matrix which transforms from a body fixed frame to an inertial frame, made up out of the multiplication of 3 independent matrices. And now the big question was about which axis was the rotations. So and the order is this psi, theta and phi. Indeed, it says ZYX, and how do we see that? And not the XYZ, as 25 you say. So how do we see that? Well, this phi apparently is about the x-axis, this theta is apparently about the y-axis, and this psi is apparently about the z-axis. Okay, next question. Then the rotation matrix BRN. So here you see cans in series, and from the inertial system I start with an angle A about the z-axis, then an angle B about the y-axis, and an angle C about the x-axis. Then I'm curious what the order of the matrix multiplications will be for the transformations from the inertial frame to the body fixed frame. So Watch out, it's not NRB, but it's BRN. So it's like rotating backwards or inverse or... Yeah, very good. So with this order of rotation, it should be RA, RB, RC, but we need the inverse, so we need to take the transpose of this guy, and then the order also changes, so this should be the correct answer. Great. So then we go to the last question, question number 5, and that's about the angular velocity matrix, R dot R transpose. And of course this is new knowledge, right? It's the topic of today. You can look it up in the book. Some of you may already know because they read the book already. Yeah, very good. It turns out to be a asymmetric matrix. Okay, that was a good one for this week. We go to the podium, Flo, 3rd place, Anonymous 2nd, and then other Anonymous 1st. Yeah, good. Some runners up. Good feedback. Gonna save the results. Direct download and save to the drive to be dead sure. Yeah, saved, so I can look at the feedback. Show the feedback. Yeah, okay, thank you. Looks good. Okay, then I stop the Kahoot. And then we go back to the lecture topic of today. So, a bit room. So, if we look at the text here, we're going to talk about rotation matrices, angular velocity, and Euler angles. So let's recall where we came from last week. So we had some coordinate system, right? Some inertial system. Usually we use capitals, but that's not necessary. And then we had a potato-like thing, and in the potato we have this particular point, the center of mass C, and then usually there's a coordinate system attached to that, which we then we call the body fixed frame. You can do with primes or Usually we donate that with primes. And that's fixed, of course, to the body. And this is, of course, fixed to the world. Then there is some point in the body P. And that point we like to trace. And how do we get to P? Well, we first move to the center of mass, to XC. And then from XC we take this local route. And we usually write that as the position of P relative to C. And then finally, how do we this is this position x of P. Or in other words, how do we get there? P is we first travel to the center of mass, and then we travel from the center of mass to point P. Now this is all vectors, and that is valid in any representation, any coordinate system. If we now want to calculate, we have to go to algebraic components, so we have to express everything in a coordinate system. So let's for now express this in the inertial frame, right? So inertial frame, then we have inertial frame, plus we have this one in the inertial frame. But we could do the same, of course, in the body fixed frame. We could say, well, we could say xp in the body fixed frame, is xc plus this xp with respect to c, the body fixed frame. Now, why would we do that? Well, there is one big advantage, and that is that this quantity, this guy, is a constant. Because the position of point P within the body, if I express that in that coordinate system, is constant. Like as I said last week, the position of my nose within my head is hopefully always the same. If I was a rigid body, it's always up front, in the middle, right? If I were flexible, it would change a little bit, but if I change my head and I don't touch my nose will always stay in the same position. So this is like constant. And that is an important thing. Now, but however, for Newton, we want to know what the position is in the inertial space. So what we have to do is we say, well, okay, we find the position of P in the inertial space is the position of the center of mass in the inertial space, plus, and then we like to use this guy, this vector in the body fixed frame. But then we have to transform these components from the body fixed frame to the inertial frame. And in general, we write that as a rotation matrix, which goes from the body fixed frame to the inertial frame. And that is the way to go. That is how we did the orientation, right? And sometimes we put primes here, or we put primes here, primes here to indicate that the components are in this system, but it's not really necessary. Okay, velocities. So this was all positions. Velocities. What can we say about velocities? Well, actually that's not so hard. We just take our vector expression and then we just put a dot on top of it. So x dot of P is x dot of C plus x dot of P with respect to C. So nothing changed there. However, I would like to use this expression. Yeah. So now I go to the component expression. So what do I say? I take this one and then I just differentiate with respect to time, right? So what do? I have these components. I want my velocity in the end frame. Is my velocities of point C in the end frame plus. Now I have two parts here, so I have to do first r dot times this vector, which is a constant, remember, plus rbn times the time derivative of this guy. But as you know, this is of course 0, because these components in the body are constant. So then we end up with this equation for the velocities. So this is the velocity equation. Now it's a bit messy, so what I actually like to do is I like to put this on the other side of the equation and say, okay, the x dot P minus the x dot c expressed in n equals this r dot b n x p c p. Okay, now this we can give another name because we recognize that as xp relative to c in the n frame. So there we say, oh, this is xp relative to c in the n frame, the dot, right? And that is actually to r dot b n xp c. Now what we notice is that we use two different frames here. Two different frames. And that is a bit confusing for the rest of the analysis. So actually we now like to have an expression about the velocities and the positions, everything in one frame. Now to get everything in one frame, we either have to transform this guy or this guy. So let's take this guy. So we're going to substitute in the equation the xb, this relative position in the body fixed frame, and we're going to write that as a vector in the inertial frame. Now what do we have to do? Then we have to multiply with this matrix R and B, right? But remember that this matrix is actually the inverse of this guy, and since it's an orthogonal matrix, it's even nicer, it's the transpose of that guy. So we could also write that as, oh yeah, that is the R and then the N B and then transpose times this NPC. Okay, now we have everything, and then we have to put it in the equation. Yeah, so we get x dot expressed in the inertial frame, p with respect to c, equals the time derivative of this rotation matrix times the transpose of this rotation matrix times the components of this relative vector expressed in the frame. So we see the velocity is some time derivative stuff times the vector, and everything in the same frame. Now, some of you might, I get sort of tired of writing all these indices stuff and so on, so I like to do more shorthand. That is drop the n and write instead of RBN, write just R, rotation matrix. I mean, there's only one thing or so. So if we do that, and then we get the following expression: x dot p with respect to c is r dot r transpose times e. Now the next step is, of course, to discover what is this. What is this guy? What is r dot r transpose? So apparently this has to do with the rotational speed of the thing, and that makes the rotational speeds, which are in this matrix, they times the position vector makes some velocity vector. If I look at this, I want to discover what they are. Now I know, I remember the following about R. And that was the identities, right? That R times R transpose is the identities. And that was because of this orthonormality. Orthonormality. But this looks a lot like that, only there's a dot. Now we can get dots there. So why don't we just differentiate this guy? So we get R dot R transpose, but we have two parts, so then we do plus R times R dot transpose is, and the dot of an identity matrix is zeros, right? And it's not 1 0, it's 3 by 3 zeros. Okay. But if I take a closer look at this, they also look a lot alike. So I see an R dot and an R transpose, and here I see a dot transpose and an R. actually it looks like this, the R dot R transpose plus, and now if I write this the other way, I get R dot R transpose transpose is 0, right? Just go through the motion. If you do this, then you end up with this. So I have two matrices. So let's call this R dot R transpose W, some matrix. And now what do we get? Then we have the following expression, that W plus W transpose is all zeros. And that means, of course, and you could also say W equals minus W, yeah? And for a matrix, it means that it is asymmetric, yeah? Then, zoom, go back to my 100. Where are they? Yeah. Minus W. And that means for the matrix, W is asymmetric. That's with double M, I guess. Symmetric. Okay, so W is asymmetric. Now W was a 3 by 3 matrix, so a 3 by 3 matrix which is asymmetric. How does that look like? So we get W. Well, if it's asymmetric and if W is, transpose. If W is minus W transpose, the diagonal terms do not change. So if something is the same, then that should be zeros here. So there should be zeros on the diagonal, that is clear. And then all of diagonal terms which are here, I need the negative there. Now I'm going to write that a little bit strange. So I write an A here and a minus A here. Now, why do I start there? I will explain in a second. Then I put a B here and I write a minus B here. And then I put a C here and I write a minus C here. Now, this fully complies with this asymmetric thing. So if you take the transpose of this guy, then what do we get? Again, these 0, 0, zeros, minus C, B, C minus A, minus B, A. And as you can see here, this totally complies. So that's good. Now, why do I write this in this strange manner? Why this strange writing? Well, if we now take this matrix W, so the 0, 0, 0, with the A, B, C, and the minus A, minus B, minus C, and we multiply it with the vector x, y, z, then the outcome is, and we just have to do the matrix multiplication, so we get minus cy plus bz. That's the first. The second is c times x minus a times z. And the last one is minus bx plus a times y. Now, a very smart mouse in the audience would immediately recognize this, right? This looks a lot like the following thing, that we have a vector a, b, c, and that has a cross product with the x, y, z. B times z times c minus y, exactly, etc., etc. So that is the cross product, apparently. So this matrix times a vector is a cross product. So in terms we could write, oh yeah, this is like a vector w cross product with x. Now the thing here, we have a nice notation for that. If we say w with a tilde, which is associated with a vector w, then that's this form, 0, 0, 0. Then here w1, w2, w3, and here the minus 1. So that is a way to write this cross product from a vector as a matrix multiplication. Tilde, notation is a way to write vector cross product as a matrix multiplication. So that's the this tilde thing. That's the thing. Okay, so back to our initial thing. So what was our discovery? X dot was R dot R transpose times X, right? And I dropped the indices now. Then our conclusion was that this R dot R transpose is some sort of tilde matrix, which by definition we call omega. So this is actually our definition of our angular velocities. Definition of the angular velocities. Omega, and omega are then the three components: omega x, omega y, and omega z. No underline omega z. Now I immediately write it as a vector, and the big thing is this omega a vector? And the answer is yes. Angular velocities are vectors. So they have all these vector quantities. So now we can write x dot is omega cross x, or with a tilde notation we could also write omega with a tilde and then just x. That's the matrix multiplication then. Now that's all very nice. We know theoretically how that all goes. We know theoretically what R dot R transpose is, that it's a skew symmetric or asymmetric matrix, that it represents a cross product, and that angular velocity is defined by that. But how do we find omega? How do we find omega from this R dot R transpose? Because that is the basic thing that we have now. Now remember that R is parameterized by three angles. Usually three Euler angles, and you can give any name to them, but we tend to have a certain, like phi theta psi or something like that. Yeah, I choose here phi theta psi. In literature you will see that there's a whole bunch of Greek names they use, and then sometimes they change the order, and it's super confusing. I see some questions in the chat. I cannot answer them now. I propose that we will look at it in the after lecture question and answers. Okay, how do we find the omega? Then, so this is the parameterization. Yeah, the thing is that these questions interrupts my flow a lot, so I cannot address them. Sorry for that. Okay, how do we get now? How do we get the omegas from this matrix? The omegas from the R dot R transpose. Well, I think it's just hard work. Because remember that the R is just as these three parameters. So then R dot is just first the R with the first angle times the time derivative of that first angle plus the rotation matrix differentiated with respect to the second angle times the time derivative of the second plus the derivative of the rotation matrix by the third angle times the time derivative. So that is R dot. But we need not R dot, but R dot times R transpose. So to finally find what the omega is, we have to multiply everything with R transpose. So what do we get then? Then we get that this is a matrix, and then times, I shouldn't put a dot there, it's a bit confusing, it's not a dot product. R transpose times phi dot plus this matrix, dr d theta r transpose times theta dot, plus dr d psi r transpose times psi dot. And that should be equal to, and let's write it out, that should be equal to this omega tilde, right? This matrix, or, and it's better actually to write that out in components so you know what you're doing. So zeros at the diagonal, right? Omega x, omega y, omega z, and then here minus omega x, minus omega y, minus omega z. Okay. Now, looking at this, if I would expand that, oh, is there an error here? Did I put a did I forget a minus? No, there's a minus there. Okay. Thank you for answering in the chat. That's resolved now. Okay. When you look at this, this is a 3x3 matrix equals a 3x3 matrix. Now, how many equations do we have? Well, we have 1, 2, 3 equations which should end up in 0. Okay. And then we have 6 equations, of which 2 are sort of identical. One is omega x and the other one is minus omega x. So in total, we are doing a lot of work to check if we are good at generating zeros, and we can check our work, because in deriving this we find both things, and one expression should be the negative of the other one. So it's a lot of work, and there is an easier way. There is an easier way. I mean, it's always good to check this, so I really encourage people to use MATLAB, what is it, symbolic toolbox, and just write out the matrices, do the differentiation, do the multiplication, and simplify and see if this really works like that. If one is the negative of the other, and if these are really zeros. So what do I mean with intuition? Oh, it's always glitchy when you talk about intuition, because then you get statements like, "You see, it's clear that." Don't you see? And it should be clear that. And those are dangerous bands. Anyway, since these are angular velocities, and angular velocities are vectors, maybe we can use those vector quantities, and there is the addition which holds for vector quantities, and by such we can find what the angular velocity is versus the rate of the angles. This is the rate of the angles. These 3 guys. Well, let's draw a picture. And the first picture I'm going to draw is, of course, cans in series. So this is a can, and what do I took the cans from the initial Euler angles, the z-axes. So I have these 3 x's. Then this is, of course, x, y, z. I can call it the inertial frame. And then here I can build this body fixed frame. Some like to call this x prime and y prime and z prime. I'm okay with that. Happy little primes, and I have no problem with that. All those happy little primes. Okay, this is then inert, right? And here we have the body. Now let's put names to them. So the first one I call phi, the second one I call theta, and the third one I call psi. Yeah. If we just focus on one rotation, then the axis is given, and we could say, oh, that is like an angular velocity. So there is like a vector here, which is like the angular velocity around this axis. So you could say, oh yeah, I know what the direction is here, and it has a phi dot. So you could say this thing is a omega vector with phi. Well, the same we can write here. So here along this line we also have a vector, And we could also say, oh, this is omega theta, right? We can write a theta dot here. So then we know what the magnitude is and the direction, and then that determines this guy. So the magnitude is this phi dot, and the direction is this. And again, here we can write a vector, which we call the omega psi. And of course, the magnitude should be psi dot, and the direction is this. But the whole problem is, of course, that all these directions, they change. When these angles are not zero, then all these directions are askew, and so it seems like it doesn't help. But we can write as a vector, in a vector way, that the omega is just the sum of these three omegas. So this omega vector phi plus this omega vector theta plus this omega vector, which is psi. And I haven't expressed it in any coordinate system. They are just coordinate free, right? Now, I do know what those vectors are in certain coordinate systems. Like, for instance, I do know that the omega phi in the n system is, that doesn't change, this hinge doesn't change, it's always in that z direction, so there it should be like 0, 0, phi dot. That is correct. Then the other one, the second one, omega theta, well, that is in another coordinate system, and maybe I should give a name to that. Yeah, becomes in the book I give all kind of names to that, but we will see in a second. So that's a coordinate system which is rotated by this. So in this coordinate system, yeah, shall I give it a name? Yeah, this coordinate system, maybe I put a slur here and F and G. Let's call it F. So at the end here there's a coordinate system F. So that omega in that F coordinate system, then we have which axis? That's the x-axis, so that's a theta here, right? And then finally, if we talk about this guy, yeah, then that is we could call it a G or a B system. It doesn't matter because it's about this axis. So finally, in the B, the omega of psi is, well, I know that's about the z-axis, so that's 0, 0, psi dot. Oh, it's not a nice psi dot. The dot is not clear. Yeah. So vector is okay. Now we have it in all these different coordinate systems. So, and I want to get it in one coordinate system, and that is doable, of course. So let's say we go to the inertial frame. So the inertial frame, the omegas is, well, this guy is already an inertial frame, right? So that is just the n omega phi. There's no problem. But then we have to add this f omega theta. And how do we get from f to n? Well, that's this rotation matrix phi, right? That's the way how we get there. Plus, and then this last one, this is this omega in the B frame. Well, we don't actually need the B frame, we need some intermediate frame here, because we don't really need this whole rotation of phi, because this axis doesn't change. This coordinate system here, G, would also be okay. So why don't we make our life a little bit easier, and not having 3 rotations but 2 rotations, and we call this G. So then I have to go change this also into G. Yeah. So here we get G. And how do we get from this to here? Well, it's of course 2 rotations, right? So we have the theta one and we have the phi one. So now we have written out how these angular velocities go. If we put in all these 3 vectors, and I will rewrite it again. So we get 0, 0, phi dot, plus, I'm not going to write out this matrix, but I'm going to put the vector here, theta dot, 0, 0, plus, and then we get r phi r theta times 0, 0, psi dot. Okay, then on the right hand side, let's write out components, omega x, omega y, omega z. So in an intuitive way, from the figure and the different rotations, we now found this expression. And that seems a lot simpler than the derivation we first had with r dot r transpose. So we can expand that. And if we expand that, then what do we get? Well, on the left hand side, of course, we get the n omega x omega y, so it should be x omega z. Then we have 3 components, right? And then we get a matrix times 3 components. But now we are in trouble, because look at it. We wrote this as a vector with this third component, first component, third component, but we cannot write it like that. So we have to find an order, and since the order of rotation is here phi, theta and psi, that is the order we're going to use to write it here. So we're going to write phi dot, theta dot and psi dot. And by doing this, by moving from this to this, you already know there is something going on with these rates of the angles and angular velocities and vector quantities. And anyway, we'll get back in a second. I have to fill in the numbers, right? Well, the numbers are super simple. In this case, 0, 0, 1, because omega z is just this one guy. And then, of course, we get other contributions from the other parts, and it turns out to be cosine phi. I just have to copy this, sine phi and a 0. And then here we get sine phi, sine theta, minus cosine phi, sine theta, and then cosine theta. And I'm going to write a big sentence here, not a vector. Dangerous band. Watch out. Dangerous band. Not a vector. Coffee break. Coffee break. Yeah. Stop the recording.